nanohub.org.
Online simulation and more for nanotechnology.
Good afternoon, everyone. My name is Sami Al-Jaloni, and I'm here representing myself and my colleague, Carrie Mays. And today I'm going to talk to you about our quest of creating everlasting electronics. So I'm going to start off by a personal story. And so I grew up in the 90s in a big family in Jordan, and we had an old rotary phone that used the old landline technology at that point in time. One of my siblings was living at the other side of the world, and she would call us every couple of months to give us her update. And my mom and the whole family would gather around this old phone and would talk for hours with her, full of emotions. My mom would cry every once in a while. Now, fast forward 20 years from that point of time, and now I live at the other side of the world, and I call my parents, who both have smartphones with video capabilities and high data connectivity. And the other day, I'm calling my mom, and I'm telling her, hey, Mom, I miss you. I'm coming next summer. And instead of like a burst of emotions, the first thing that I get, what are you doing that? Save your money for college and keep it for your kids. And I can see you over the phone just as if you're sitting next to me. So why spend that money? So anyhow, look how come we've developed and we've came in our technology. And this is all or mainly due to the development in the underlying chips inside of our phones, the reliability of electronics inside of it. Another great example that showed how electronics that we see in every day, each day, help facilitate technology is actually the electrical vehicle, the EV. You see today, if you look into a parking lot, you see 3 cars, EV, as an electrical vehicle. And 12 years from now, you'll see full parking lot full of EVs. And this growth is going to put in a lot of strain on the reliability of electronics as the demand becomes more into there's more high power applications that will demand more reliable electronics. So if we, to put it into bigger perspective, here in this slide you'll see time versus the projected increase in power needs for various applications that we feel every day. So you can see roughly every 10 years our need for more power and for electronics, reliable electronics that can support the more power needs is going to increase even like 10-folds every 10 years. So there's a lot of applications that needs reliable electronics, and it's going to become more challenging as we progress throughout the years. So to put things closer to perspective, if you open up your EV and look inside of it, and then zoom in even further to an internal chip, and then even zoom a little bit further and pick up an individual device, a transistor, or a power electronic device. Those devices typically have wires, connecting wires in the sizes 100 times smaller than a human hair. And those with high enough power, they make our wires and interconnects fail. So how can we make this more reliable? And the failures here happen due to electromigration. So what is electromigration? Think of a flowing river pushing rocks down its way as it's fiercely has a lot of force in it. It's the same as electromigration, but instead of water, we have an electrical current that pushes atoms from one side to the other. Now, this is a 3D microscopy image that we obtained from one of our devices, and the height here of the device is exaggerated. It's actually 1,000 times smaller than a human hair. So if enough atoms get displaced, as we can see from here, it's going to there, eventually the device is going to fail. So what can we do to make these devices more reliable? Well, what if we could make these devices self-heal, as what we see in nature and the human body? Well, what if we add a bunch of rocks to the side of the river, and with enough amount of force of the current, we can drive some of the extra rocks or atoms to fill in the gaps. So if we have a failure like this, we could hopefully prevent this failure by having atoms fill in this gap. That's what we're aiming to do, and that's what we have in our lab, is high microscopy, high resolution microscopy that enable us to get a lot of data and monitor the development of electromigration. We get optical data plus thermal data and a bunch of other parameters that help us get into the next phase of designing better wires, better electronics that can last forever.
All right, we're fine.
Okay, thank you very much.
So, good afternoon, my name is Lucia, and today I will be introducing the concept of liver on a chip. So I was trying to explain the same concept to my dad, and I was on the phone, and I asked him, Dad, what if I told you I had an hemorrhage, like an internal bleeding in my stomach, and what if I told you you could have it too? And he asked me, why would I have one? I was, well, you had an ibuprofen, you might have an ibuprofen last night, or like not long ago, and it's one of the side effects. It says it on the leaflet that comes with it, and it comes with a lot of other side effects, and this is just for ibuprofen. What if it was a very novel cancer treatment? So the currently available methods that we have to test drugs are animal models. So if my dad and I don't react to the same way to the same, we react a different way to the same drug, a rat is going to do it a completely different way. And the other method we have is 2D cell cultures. So 2D cell cultures are petri dishes, and inside these petri dishes we culture the cells. We provide them with nutrients and chemicals, and we expect them to react the same way as they do in our body. So in our body, the cells are in a very complex environment. They're subjected to different mechanical forces. They're subjected to different chemicals, and they are arranged in different geometries. So I'm currently working on a liver on a chip, and this is the liver. We could, in a simplified approach, we could imagine the liver like sheets of cells that are intercalated with capillaries. So the way we've thought about resemble this structure is with a paper-based liver on a chip. So it consists of cells cultured on top of papers, so that's square, and we stack them. We separate them with a frame made with a frame, so they're not in direct contact, because in the liver they're not in direct contact. So we make them be separated from each other, and we stack them together with filter paper. So this filter paper is like the one you use to make coffee, for example. And if you rinse a filter paper with water, it would go up. So this is called capillary action, and this will resemble the capillaries inside the liver. So the final device looks like this, and is made of 3 layers, and the middle one has a hole in it in which we'll introduce our liver. And they will be stuck and screwed together and assembled in this way. So as you can see, it has two tubes placed on it, and so by these 2 tubes we'll be able to monitor what chemicals we want to inject in the liver. We could also monitor the pressure difference between the inlet and the outlet, and basically mimic different conditions for different diseases, test different drugs for each patient. So it has 3 main applications. So we could study the side effects of drugs. We could tailor patients for each patient, and also we could study diseases at the cellular level. So organs on a chip have a lot of improvements. It enables us to resemble the conditions inside an organ. It also enable us to monitor the environment inside the chip, and our liver on a chip it's a very simplistic approach, and it's also unhelpful for the patient, because the cells we collect are from the patient, so they have their genetic information. So thank you very much. Any questions or opinions?
So, good afternoon everybody. My name is Avik Datta,
and today I'm going to talk about my project, which is titled Solar Nanoprison. Now, my project is about clean energy. Now, and you might have heard of clean energy in the context of climate change. Climate change is a topic which has been covered extensively over the past few months by the so-called quote-unquote fake news media. And one of the recent topics which made big headlines last month is that the world is on course for a 3 degrees Celsius rise in surface temperature by 2100. As it is, we are at 1 degree Celsius above what the temperature was at the turn of the last century, and we are already seeing rising sea levels, and the number of natural disasters has increased, which meant that from 100 million people affected by natural disasters in 2015, the number doubled to 200 million in 2016. If you have a surface increase in temperature of 2 degrees Celsius, then an additional 400 million people are susceptible to heat waves. With this in mind, the United Nations has put forth a new idea to reduce carbon emissions to zero by 2050. And in order to implement this plan, they have called for a $2.4 trillion per year investment in clean energy for up till 2035. Now, I'm a greedy person. I want a share of that pie. Okay? And I'm justified in making that claim because the aim of my project is to improve the efficiency of clean energy production. So how do you produce clean energy in the first place before we go into efficiency and improving efficiency? One of the biggest resources which has been researched widely for clean energy shines on us for half the duration of the day. I'm of course talking of the sun, which throws in 100,000 terawatts of energy on the Earth's surface. How much do we use in a year globally, all across the world? About 10 terawatts. The number is 18 terawatts in 2014, 16 in 2013, something around that. So the question is, can we store this intense amount of energy? How do we do that? Is there a possibility? The answer that the world has widely accepted is we can store this energy in hydrogen. Hydrogen is the most common element found in the universe, and here on Earth, it is abundantly found in the form of water. So the question is, how do you turn sunlight and water into hydrogen? And here is how. You let sunlight shine on a material called the semiconductor. What the semiconductor does is it takes this sunlight and converts it into positive and negative charges. Now you take a couple pieces of copper wire, stick it into that water bath, and you allow those positive and negative charges to flow through those wires. You are passing electricity through water, middle school physics experiment, and you end up getting oxygen and hydrogen. Everybody knows that. Okay, so that solves the problem, right? No. The problem here starts the problem. The process that I just described is not as efficient as you would want it to be. And one of the places that you can look towards improving the efficiency is this semiconductor material. Can I do something so that this semiconductor traps majority of the light instead of reflecting it or transmitting it? And can I convert majority of the trapped light into that positive and negative electron charges? That's all this is about. So the question is, can I improve light trapping? For doing this, I turn to a field of science called plasmonics. The name might not be common to people in the audience who do not work with so-called photonics or optics. What is it about? It is about metal nanoparticles, 10 nanometers sizes, 100 nanometer sizes, and stuff like that. And what happens when you shine light on these metal nanoparticles? The answer is you can trap light into nanoscale dimensions. And not only that, you can increase the intensity of light by 10 times, 100 times, 1,000 times. If you don't believe me, here is a research paper. Okay? Because everything is true in a research paper, right? So you can see that this gold nanoparticle has been able to trap light, green light here, and red light in that tiny dimension. Now, this is, you have to believe me, that, oh God, I took that same principle and I converted into this design. What I have a semiconductor, 15 nanometer thick, which is iron oxide. I designed gold nanoparticles on top of that. And I studied what the gold nanoparticle does. For the solar energy, which the iron oxide absorbs very much, I could increase the efficiency by 2 to 3 times. And I got a 6 to 7 times increase for wavelengths where even the material was not that much responsive. So even though the overall efficiency turned out very low, my point is that numbers are on top are the key factor in this case. The final efficiency that you see here is low because the iron oxide film I started out with is very poor. The message that I want to throw you is by using these techniques of plasmonics and metal nanoparticles, give me your best looking or best performing metal films or semiconductor films and I can make them perform better. So that's the message that I want people to take away from this talk. Thank you very much.
Good afternoon. My name is Oluseyi Kamalede, and I am here to discuss an exciting project that my friends and I are working on. We are working on a room temperature qubit for quantum computation and secure communications. So, to begin with, before we talk about this weird quantum stuff, let's talk a little bit about bits and classical computers. We're all very familiar with classical computers. They are everywhere. We have cell phones, we have laptops, we have computers inside of our toaster ovens and things like that, you know. Everybody knows about a classical computer. And classical computers are made of what are called bits. And a bit is a unique little device. It can only be in one state at one time. Where a quantum bit, which is what makes up a quantum computer, kind of gets around this limitation. You see, a quantum bit is able to be in many states at one single time. And that's because quantum bits can access what is known as superposition. And superposition is just a really fancy, sciencey way of saying that a qubit encodes a lot more information than a classical bit. And this is a really amazing result. This is a fundamental result, and it's so fundamental that it has actually paved the way into making quantum computers a billion-dollar industry, multi-billion-dollar industry. And that is because we have countries like China, like Australia, and like our own US of A, investing several $billion into quantum research. And the reason why they're doing this is because quantum computers have so many applications. For example, you can have ultimately secure communications using quantum computers. If you have a quantum computer on this end, quantum computer on this end, and somebody tries to eavesdrop on that communication, by the very nature of their eavesdropping, they will alter the information being sent between the both endpoints, and both users will be able to know that this conversation is being eavesdropped upon. This is what makes this is just one of the several applications that makes quantum computers so attractive. So, there's a catch, and there always is. All across the planet, all across the entire world, everyone is trying to make these quantum computers and quantum bits, but the one key flaw is that every single one of them has to be operated at cryogenic temperatures. I'm talking a couple of degrees, just shy of absolute 0 Kelvin, okay? Really cold. Our device works at room temperature. So let's talk about it. How does it work? Well, our device basically acts as a single photon source. And what does that mean? It means that it emits a single photon. Well, what is a photon, Shreya? Well, a photon is a single particle of light. And right now we are being bathed in photons, okay? And a single photon, what that is, or what that does, is it is the basis for our computations. So I'll continue. What does a single photon source look like? How do we design one? Well, here's our proposed design. We have a xenon impurity within some nanodiamond, which is a very small diamond on the order of 20 nanometers in diameter, surrounded by a silicon outer shell. The basic operation of our device is we will excite it with a laser, and then out comes our single photons, which we can use as our fancy quantum computer quantum bits. All this is occurring at room temperature, I like to stress. So the key thing that we need to do is we need to make sure that this device will actually work, okay? Like, it's nice, you know, we got some xenon, diamond, whatever, but this thing needs to work, all right? So we've gone ahead and we simulated it. And what are the results? Well, the results are very promising. Here's our result. As you can see, we are exciting our device right here. And this pulse, what that's showing you in fancy science diagram, is that we are actually able, in simulation, to prove that this device is capable of emitting these single photons. So the path is clear, we're ready to go. All that's left is to build this device, and that is what I am currently working on. I am actually building this device, and I have a unique challenge, okay? I've got to get xenon into a diamond that's really small, okay? I have to, this is kind of crazy. How do I do that? Well, I'll tell you how I'm doing it. I'm actually making a thin film of nanodiamonds on a quartz wafer. And then I'm taking a big ion gun and I'm shooting ions into the diamonds on that quartz wafer. And then afterwards, I'm just growing a nice little shell around those diamonds, and that will get you that device that you see right there. That is our single photon source. The way is clear. So in closing, we have talked about the fabrication, the simulation of this wonderful new room temperature, I've stressed that, device that will change the world. And with this device, what that means is, at room temperature, it means that you can have a quantum computer, you can have a quantum computer, and you can have a quantum computer. And as this technology grows, as it matures, it will really change the world. It will help us do things like solve world hunger. We will be able to manage our energy use, and we will be able to have secure communications, like I mentioned previously. Welcome to the new era, ladies and gentlemen. Welcome to the new era of room temperature quantum computers. Are there any questions?
Good afternoon, my name is Alexandra Loaiza. I am a PhD student in materials engineering. A little bit about my background: I am materials engineer also, and I have a master in materials engineering. Today I'm going to talk about phosphide sensors, applications, and approaches. First of all, let me introduce you with the main character of my history. He's Juan. Juan is a farmer. He's growing carrots in his farm. He's the main producer of carrots in a small village, in the small village where he lives. But he is also growing, doing fish farming. So, because this way of farming fishes is the fastest way of producing the consuming fishes. Around half of the fishes that are consumed are produced by this method. So Juan wants his carrots to be bigger, and he wants to get more production. Why? Because the population in his village is growing, and it is expected by 2050 that the population is going to be around 9 billion people. So the current production systems are not going to be enough at that time for the population. So he wants his carrots to be bigger and to have more production, to be according to the growing of the population. What is causing? He's applying fertilizer in his carrots. That is getting growing his carrots because fertilizers are compounded by nitrates and phosphates. Nitrates and phosphates are present in DNA and in many biological processes. That's how fertilizers are helping his carrots to be bigger. But one day, his fishes died. He was asking why. So the answer is that as he was applying fertilizers contain phosphates in its dibasic and monobasic forms, and that is causing the death of his fishes because it's causing eutrophication, and eutrophication is a atypical growing of algae in the aquatic bodies due to the excess of nutrients in the water. So it goes to through the soil, goes to the water. Then it's increasing the nutrients, then making growing the algae, and then because of the lack of the light and oxygen in the rivers, it is causing the death of those of the fishes, of aquatic life in general. It is calculated that the contamination by phosphates are around 50% by sewage wastes, 40% by agricultural activities, 10% by mining and industrial activities. So for this problem, we want to develop a phosphate sensor, which is measuring the concentration of the phosphates in water and soil. In our case, we are using a sensor functionalized with nickel, and it's going to give, in the surface of nickel, it's going to give a compound with the nickel, which is called nickel phosphate, and that is going to give the sensitivity for our sensor. Questions?
So good afternoon, everybody. My name is Jose Guaymin. I am part of Dr. Rahimi's group, first year PhD student here, and I'll be giving you my presentation on detecting microbial activity for agricultural purposes. So first of all, why do we care about detecting anything in agriculture? So as the demand for food grows, there is a demand for bigger fields to produce more food, right? That makes sense. However, we're expecting for farmers to measure way more data in way bigger fields, and that just seems highly unlikely. So that's why we turn ourselves into sensors. Sensors are able to measure the different parameters that the farmers need to produce the highest yield of food, all in their hand wirelessly. However, as the fields increase and the necessity for food, the demand for food increases, the use of fertilizers and pesticides also increased. The problem with excess fertilizers and pesticides, especially synthetic fertilizers, is that this will leach into the groundwater, go into the soil, and they'll ruin the soil quality, and they'll also ruin the soil by bacterial activity. One of the negative effects, as my colleague actually was showing, is the appearance of red tides off the coast. So this excess nitrates will go into the water and create this. This is like overgrown algae in the oceans that turn this red color. Now, this is not just a local problem, it's a worldwide problem affecting all the red zones. These are all hypoxic areas, which means they're completely depleted of oxygen, which leads to this massive death of fish and any other marine life that needs oxygen to thrive. So this is like a worldwide problem that can be easily solved with sensors. Now, how does this tie to bacteria? As I said, it's the use of synthetic fertilizers, pesticides, heavy pesticides that are causing this negative effects. If we use organic fertilizers, we can use natural ways of creating the sufficient nutrients that we need, and also use biological ways of getting rid of the excess nitrates. Some bacteria that we use is actinomyces, which are degrading bacteria that we need to decompose the organic matter that we need for these fertilizers. Nitrifying bacteria, which they naturally convert nitrogen, which is free in the atmosphere, into nitrate that the plants can use. And denitrifying bacteria, which are especially interesting to me because they can actually take that nitrate and turn it back into nitrite or ammonia, which has no negative effects on the environment. Close enough, don't quote me on that. So the in-situ commercial sensors that are available now, they usually focus on measuring nitrate, phosphate, potassium, or organic matter through optical measurements. There's not really any sensor that measures bacterial activity in the soil right now. Any lab measurements or lab techniques use optical density probes or big machines like that one that require large samples, using of bleaching samples to measure bacteria, and you end up measuring dead bacteria. You are not actually measuring live bacteria in a live environment. What we are using is, we're using liquid cellulose acetate. So we're using this liquid cellulose acetate and creating a film. We're depositing this film in an interdigitated electrodes, so meaning electrodes in this conformation, pretty much. And we're putting them in a solution with bacteria. Simple as that. Now, the output of this is, we see an impedance change. Impedance is an electrical measurement that measures the resistivity to flow of current. And I like to see it as a universal way of measuring different circuit elements. So right here we have an example of a interdigitated electrode with a circuit model using different circuit elements. So the idea is that we'll take one unit, one measurement, change in impedance, and by doing so, by measuring the impedance with a full covered layer and the impedance with no layer, we can measure the change in that impedance as the film degrades. Now, what I like about this technique is that it's based off on a very used technique, which is putting cotton fabric in the soil, leaving it there for months, taking it out, doing tensile testing, and that will give you bacterial activity measurements. This has been used for hundreds of years from what I've seen in the literature. And what we've essentially done is use the cotton fibers, which are 96% cellulose, found cellulose acetate, which has the same backbone made from glucose, and pretty much digitalize that into an electrode that can give out electrical measurements. The features of this sensor is it's very low cost, easily reproducible. It can be made into a roll-to-roll manufacturing, and it can be hooked up to LoRa modules that are being used right now in our research to wirelessly transmit this data into a receiver and into the hands of the farmers. These are my key points, and if you have any questions, thank you very much.
My name is Beatrice, and well, you've probably seen this title a lot of times. Next Step Fighting Cancer. It sounds cool, it sounds amazing. But I can assure you that what I'm going to be talking about, you haven't heard it at all before. So a little bit of biological background, so you understand how, like, the concept we're studying here. So the extracellular matrix is basically the space we have in between the cells. We have different components, and some of them are proteoglycans, proteins, others is fibronectin, collagen have structural support. So all of these components are key when looking into the actual functions of the extracellular matrix. So the functions of the extracellular matrix, we have cell adhesion, cell migration, cell proliferation, and cell differentiation. So, proliferation has been proven to be one of the key factors when looking into cancer development. So, like, when you have cancer, you have uncontrolled proliferation of cells. So, a few studies have been carried out that have actually proven that tumor cells do actually produce a higher number of proteins and glycans into this extracellular matrix. So, the fact that they produce more components will make the environment of the tumor cells stiffer. And this leads us into our motivation, why we want to measure this stiffness. So right now there's this great need for platforms that can actually monitor this change in mechanical properties in the cell's extracellular matrix. And it has two main applications. It can monitor the change in the stiffness of like, you can compare it with between healthy cells, tumor cells, and just see how the stiffness changes with different types of tumors and stuff. But more importantly, it can monitor the effect of drugs in cancer treatments. Like, you can test the different drugs and see the effect on the stiffness of the environment. So there are other methods that are being used, are, for example, atomic force microscopy and universal testing machine compression. The problem with these methods is that they're very disruptive to the environment and don't allow to perform in vitro monitoring. So our device actually solves this problem and allows us to monitor in vitro, monitor the actual cell's stiffness without disrupting the gels. So our device has three main components. It has a signal generator, piezoelectric material, and an output signal. So the signal generator will introduce current into the system. This is the system. Then we have the piezoelectric material that will go on and talk a little bit more about that afterwards. And then the output signal, that's basically a voltage that we get, and we will correlate this to the stiffness of the gels. So piezoelectric principle, basically what a piezoelectric material is, if when you introduce current into the piezoelectric material, it will be able to generate an ultrasound wave, and then also the same material, when it receives ultrasound wave, it will be able to generate an output voltage. So this is basically what the principle we're using in our device. So we carried a few experiments. These are the piezoelectric materials. Here you introduce the current, here you take the output signal. And we use water as our control, and we introduce different agarose gels with different concentrations in order to look at the different stiffnesses and how this would impact the output signal. And so we perform different tests. We have the mechanical stress, so we can know the different stiffnesses of the agarose gels that we're implementing. And then we have the acoustic impedance. And the acoustic impedance, it's basically measuring the time it takes for the ultrasound wave to go from one piezoelectric material to the other one. So imagine you're the ultrasound wave, and you have to go from one material to the other. So in the case of water, it would be like traveling in a plane field without any obstacles or anything, so it would be pretty easy, you would say. But when you have a stiffer gel, it would be like traveling through a forest with loads of trees, so it would probably take you longer. So that's basically what we're measuring here. So when looking into implementing this into drugs, like into tested drugs and the effect of drugs, what we would do is we would implement a microfluidic channel, which is just a channel that contains the drug. The drug would diffuse into the hydrogels. We would see like the drug will interact with the cells, and we will be able to monitor this change and see how the drug does it. So basically, the take-home message is our device enables you to perform continuous real-time and in vitro measurement of the change in cell stiffnesses, and it can be key in cancer treatment analysis. Thank you.
My name is Armin. I'm from Materials Engineering Department, and I've been working on this for the past 2 years, and we filed multiple patents on this advanced sensors and loudspeakers. So first of all, why is it important? So we all talk about this really important Internet of Things, which can be described as a smart network where every electronic device will be connected in the near future. So by 2020, it's estimated it's 34 billion. This includes smartwatches or industrial devices and everything. But you cannot do this without sensors. You need some like smart sensors, first of all. And piezoelectric sensors are one of these sensor types, but they have one advantage over the others, which is the harvesting energy. So these sensors are self-powered devices. So as explained in the previous slide, it's a well-known technique to piezoelectricity. So you apply pressure, you basically create a tiny battery inside the material. It's like this. You apply pressure, you generate electricity. So, but there are drawbacks of the current technology. As you saw in the previous presentation, those sensors are like rigid, and it's not really compatible to integrate them into flexible electronics. And if there are some recent advances, they're flexible now, but they're not sensitive enough. And even if they're flexible and sensitive, but they're too complex for continuous manufacturing. And we all know for every product in the market, if you wanted to go to the consumer, you got to make it in large scale to make it low cost. But here right now, it's all high cost. So what we produce actually, it's a flexible, transparent, not just sensitive, ultra sensitive, and the largest piezoelectric film ever produced. So I'm going to share the cost too. It's a low cost. So our sensors, I'm not going to go into detail about the technicals. The flexible and transparent, you can see up to 90%. And it can detect the bird feather, actually. You can see the bird feather. It's a high-speed camera. You're dropping the bird feather on the sensor, and you're going to see the signal appearing here. So, and okay, a little bit more pressure, let's say finger tap. It's 8.2 volts, which is 20 times higher than what's reported in the literature. So out there, this is the best out there. This is 20 times more efficient. So large-scale manufacturing. And here another sample from the literature. They consider 30 by 30 centimeters large scale. And here's our sample, the largest ever produced, 10 feet long, 6 inch wide. And this can be longer than this. You only see the portion of this here, and it's semi-transparent. So it's a low cost right now. With cost analysts would figured out that this is the, for the next 10 years, right now it's around like 80 cents. In 5 years, it's gonna be around like a quarter, a square inch sample. So the possible impacts on our daily lives, low cost wearable health monitoring systems, high performance touch screens. This is where it's going to play the transparency role. Structural health monitoring systems, not for just our health, but buildings and all the structures needs health monitoring too. Because we had this terrible accident in Miami in March where 6 cars crashed underneath the bridge because of this lack of these sensors. And also more efficient energy harvesting systems, like Bridgestone is making these tires for energy harvesting while you're driving on the road, or tiles, or some futuristic ideas like smart wristbands to control drones, or some electronic skin applications. And a loudspeaker. So in the previous presentation, you may remember there are two effects of piezoelectricity. So you apply pressure, you generate electricity. But the reverse effect, where you apply electricity, you generate silent vibrations, loudspeaker. Most of you here actually seen the demo during the afternoon session. But here is the speaker that we created. It's basically, it's transparent, sitting in front of a laptop. And here is my favorite song, one of the from Frank Sinatra. It's basically the same sensor as playing the music. Yes, film. It's basically flexible, a thin film that acts like a speaker. So decibel levels we measured right now, it's around here, CD street or loud radio, and covers the whole humming range frequency.
So no magnet,
Nope, that's the magic. So here are the impacts. TV screens can act like a loudspeaker, that you don't need external speakers. Or windows that can act like a speaker, it's transparent. Or microphones, self-read e-newspapers, active noise cancellation for cars. Even this projection screen can turn into a loudspeaker. So to conclude, we had one material and multiple opportunities for future create.